Okay, hello class. Section 2.5. We're going to talk about especially tractable cases for improving search. So our improving search algorithm, start with a feasible solution, find a direction to go in that is improving and feasible. We'll figure out how far we go in that direction, get to the next iterate, and repeat. Always making improvements at every step. And there's a couple cases that are especially, remember tractability, ease of implementation, ease of finding the solution, where this is particularly good, that algorithm. But let's talk about what are places where it could fail. So the improving search, we've already talked about this a little bit. You could get stuck in a local min or a local max. Let's do the steepest ascent problem. So we could have a surface and then there's another one over here. So improving search, we could come iterate, and get up to this local max over here. But, and we think there's no room for improvement because remember the algorithm 3A, improving search, that box, if there's no improvement, stop, you're done, you turn that solution. All you can say though is that's the best found yet. And you didn't even know about this one over here, this local max. So we talked about you could restart and do the hill climber. So what happens is it has problems when it gets caught in local extrema or in saddle points. And let's just think about, well, when did it seem to do good? What were cases where it was guaranteed to find the global extrema? Well, those could be cases where the surface is particularly simple. Maybe it's just that downward facing circular paraboloid, right? That was like, or in general, z is a function of x, y, ax squared plus by squared. Right, so that's opening. So let's maybe add a constant and put it down. C minus, makes more space so you can see better. Downward facing, paraboloid, elliptic if the A and B are not matching, circular if they're matching. So this one has every local extrema, there's only one, is a global extrema. So it works well on this unconstrained problem. But remember, we also are going to have constraints. Think back to that D club example where the feasible region looks something like this. We were trying to avoid some population centers and then we were everywhere else is the feasible region. So the surface, once you add that constraint, there's a surface over that. If this is the axis coming out from the board, well, there's a surface over this. And that had a couple peaks. I think there was a peak over here and then a lower one down there coming out from the surface. So then that surface actually has parts of it removed. And when you add the constraints, then some of these cases that seemed simple before, when they could become constrained problems, become much harder. So again, it looks like in general for improving search, it's not going to be an all-purpose. It's not going to work on most problems to get you guaranteed to a global extrema. It'll get you something good, but the best there's no guarantees except in special cases, and that's what we're going to talk about here. There's special cases when related to the objective function. When the objective function is unimodal or something called, or our linear objective function, this guy is especially tractable. And then we're going to talk about the constraints. When the constraints have certain properties, those combine to make a very tractable problem for improving search. In fact, you can guarantee if the objective function satisfies certain conditions, the main one that we're going to use is if it's linear. And if the constraint set satisfies certain conditions, the main thing being it's convex, those two things hold, then you're guaranteed improving search is going to get you to a global extrema. That's amazing. That's fantastic news, right? So let's talk about why that might be. The linear objective function is so tractable for this reason. First off, remember that a linear objective function is just some coefficients in front of some x's. So like, for example, it could be, let's put it in numbers. Like 2x1 plus 3x2 minus 4x3, right? That's linear. The c vector is 2, 3, minus 4. The x vector is x1, x2, x3. So we can really write it in our compact notation as it's just c dotted with the x vector. It's harder for me to boldface on this board, but that's what the little arrows on top. These are vectors. Well, let's think about something from the previous lesson we learned is that delta x is improving if the gradient dotted with that direction vector is greater than 0 for a maximization problem. Well, it's really easy to take the gradient of a linear function. You're just pulling off the coefficients, right? The gradient is the partial with respect to x1, partial with respect to x2, partial with respect to x3. That's just the c vector. So all we have to do to check for improvement in our direction vector is c dotted with delta x. So easy computation, easy to check. But here's where it gets a little bit better, is that this delta x remains improving. So once you find an improving direction, it remains the improving direction at all feasible x. And thus, when we're trying to get the step size, remember at a point, we have a direction, okay, this is an improving direction. That remains improving all the way until you're no longer feasible. So you can actually run all the way to the edge of a feasible region. If you're, on the other hand, if your surface was linear over top of this and you start improving, it's possible that you actually are no longer improving, right? It's just the fact that because we're linear, we can go all the way to the edge. The only thing we really have to consider in the step size, lambda, is the constraint set. And we'll see that we're going to work through some algebraic examples here in a moment. Okay, I'm going to erase the board and we'll get to the next case. That all has to do with the objective function. Having a linear objective function is amazing, simplifies things. It makes us have a good chance at improving search, giving us a global extrema, as long as we combine it with something with the constraints, which we're about to do next. Okay, we're going to now focus on the constraints. So we said that if the objective function is linear, that's good news, that's especially tractable. Another case that we're not going to study, but just to give you a little extra information, is if the objective function is convex, which means for any 2 points in the surface, so imagine a paraboloid opening up, pick a point, connect them with the line segment. If that lies above, within the surface, then it's convex. So if your objective function, your surface is convex, that's good news. That makes a whole nother class of programming called convex programming. I actually have a whole book. Looks like not here. It's in my office proper on campus. Convex programming, again, entire textbook associated with that, because that is another class where having that property that the objective function is convex opens up whole avenues to different algorithms. For us, we're going to focus on the simplest case, which is linear. So if our objective function is linear, check, very good news. Now let's check our constraint sets. The property we're looking for here is if our constraint set is convex. That's really good news. Linear objective, convex constraint set, excellent news. So what does it mean to be convex for a set? A feasible set or feasible region is convex if the line segment between every pair of feasible points lies entirely within the feasible region. All right, so let's think about a few of these. I'll draw a couple, then you're going to draw a couple of convex and non-convex. Oops. All right, so something like this would be convex. I pick any 2 points in the feasible region, draw a line, they're still in there. Any 2 points, just draw a line, they're still in there. Right. Non-convex, maybe I have something like this. My feasible region is everything inside this little arrow shape. Here's a point, that's within it, but here's a point and here's a point, and they're outside of it. So non-convex. That needs to hold for every 2 pair of points that I can pick in the feasible region. Okay, so pause the video and draw a couple more yourselves. I want you to draw in 2D and 3D, a couple examples of convex and a couple examples of non-convex in both. Okay, so some more convex ones. Any polygon would work. Actually, a line segment, if that was the entire feasible region, pick any 2 points in there and they're still within the feasible region. Non-convex, we actually looked at this one with the hotel. We were building a hotel with floors. The feasible region was this, just a line segment that was non-linear. You know, any 2 points are not in that because you actually leave that segment right there. And here's another one. We've seen some of these. We could have a discrete feasible region, clearly non-convex. But again, there's some special cases here that make these doable. The most trackable though is here when you have a convex set. And then in 3D, just an example we've talked about before, is a linear set of constraints. In R3, each one of those could be something like a plane, like x1 plus x2 plus x3 less or equal to 4. The face is given by the equals 4. Maybe you had x1 minus x3 greater than or equal to 1. X1 greater than or equal to 0, right? All these half spaces intersect and create. They're all, each one of these is linear. The equality makes the face, the plane. So all these intersect and create the feasible region, which is a polytope in R3. This is convex. Any 2 points in or on this polytope, the line segment is within those. So feasible region, and then if we add on top, the other good condition is if we have a linear objective function. So if there are 3 variables for something like this, let's say we had an objective function like minimize a function of x1, x2, x3, which is 2x1 plus x2 minus 4x1, right? So linear, good news, linear program. And why is that such good news visually? These are really in R4, so that's a hypersurface. And these are in R3, that's what we described and could visualize. But we can draw the contours of the R4 surface as R3, set this to different K values. So clearly that's a plane that marches through at different K values. Different parallel planes are going to come through and slice through this. And linear objective function moving through a linear feasible region that is convex, best case. Okay, let's see. Oh, so it's easy. It's nice when you can visualize them in R2, easy to draw one or the other. Also in R3, you have some facility to do that, but we're going to need an algebraic definition to define convexity because that's only going to take us for little toy problems, right? So let's do that next. Okay, so to get to our definition of defining an algebraic definition of convexity for Rn, let's review something from Calc 3. So the line segment between 2 points, x super 1, so we're in n-dimensional space here, so this is an n-dimensional vector. If we wanted to be in R3, this is a point in 3-dimensional space. This is another point, and so we have a point and a point, and we want to get the line segment between those. Well, that's actually defined algebraically this way. We're going to have a parameter lambda. Sometimes in Calc 3, you might have parameterized with t, so a space curve t. Lambda is going to range between 0 and 1. And we're going to take the point we started at, x1, and then take this as our direction vector. So look, this is just like our update row, right? This is like our delta x right here. And we're going to go some distance lambda, and we're going to let lambda vary. If lambda is 0, we're just at the point we started at, x1. If lambda is 1, we're at x2 because those x1s cancel out. And this definition works in Rn higher dimensional space. At a point, this is the direction we're trying to get to this one, so we're going to make a vector between those two, and then we'll go some distance, and that distance we're going to traverse ranges from 0 to 1 to get us to that point. So we can look at this in Calc-Plot 3D just to share the screen and show. Okay, so I entered a couple points. Here's our point, just made up a point 1, 0, 0 that we want to start with. This one is in red here. The red one, and then this point 0, 2, 1 is in blue. We want to go between those two, so we can make a vector between those. That is just x2 minus x1. So when I subtract the second point 0, 2, 1 from the point 1, 0, 0, I get the vector minus 1, 2, 1. But I want to start at my initial point, the red one. So I enter that. I have this green vector, right? And that, to traverse that entire thing, you actually could enter that as a space curve starting at the x1. So in our notation from Calc 3, you usually parameterize with t. That's what Calc-Plot 3D is going to need. What did I say the first point was? 1, 0, 0. plus t times our direction vector, which was -1, 2, 1. And so we can create this vector 1 minus t, 2t, and t. If we enter that as a space curve in Calc.3D, add to the graph, space curve, r of t, replace the preset one with ours, 1 minus t, 2t, t. And we can make t go from 0 to 1. And let's get rid of the vector in green and replace it with this space curve, which we can change to a color. We made it red, that's fine. Okay, so that space curve, but what happens, I'm wondering in this parameterization t or lambda in the formula over here, if instead of going between 0 and 1, you go between 0 and 10, let's say, or 0 and 2, what happens? What do you think? Pause the video, take a moment, and then we'll show you. Hopefully you have a good idea. It's just going to sail past the blue point for another length of 1. We'll go up to here. So let's see what happens. We hit enter. Yeah, so there we go. What happens if we went from -1 to 1? We're now going to go back in this direction a bit. And so you can go from 0 to infinity, and that makes a ray. So if we went t from 0 to infinity, we'd make a ray shooting off this way. If we went from 0 to negative infinity, it'd make the ray shooting off infinitely that way. From minus infinity to infinity, it creates the entire line. So we can define a line, a ray, or a line segment, all with that formula. All right, so again, that's going to be super helpful geometry for us when we think about this algebraically. Okay, so let me erase the board. The next part. Okay, again, we've mentioned this. We've talked about visually and geometrically, it made sense to us that linear constraints of this form, ai dotted with x less or equal to bi, or they could be greater than, or they could be equal to, or any combination of those. Those form a convex set. They do. And visually, we talked about it. It's the intersection of a bunch of hyperplanes which form a polyhedron. And so if we're in R3, or let's say we're in R2 first, maybe we'll start there. In R2, intersection of inequalities and equations might create a feasible region, something like this. You can tell that right there. Convex. In R3, planes, planes, planes. We've had this discussion of this polytope before. And that's a polyhedron if it is unbounded, and when it's bounded, it's called a polytope. So that's the word I've been using a few times. Right. So this is a polyhedron that happens to be a polytope, right? Because it's bounded. If it was going off infinitely in some direction, then it's a polyhedron. Okay, let's prove this though, that linear constraints form a convex set. So without loss of generality, let's just focus on one of these types instead of all of them or a combination of them. Let's just say ai less than or equal to x, ai times x less than or equal to bi. So just the less than inequalities. And to show that this is convex, I need to pick any 2 points. So let's just use some notation, and we'll call it x super 1, x super 2. Those are 2 points in the feasible region. By definition, because they're in the feasible region, then they have to satisfy those constraints that are less than. So ai x1 is less than or equal to bi. ai dotted with x2 is less than or equal to bi. All right, what we need to show though is that the line segment between those two, okay, sure, you say they're in there, good, there's 2 points in the feasible region. We now need to show that the line segment between those 2 points is also in the feasible region, any point along that line segment. And I should say, right, this should be specific here for 0 less than equal to lambda less than equal to 1, right? And so another way of saying that is we need to show to be in the feasible region that it satisfies the constraint, the less than or equal to constraint for every constraint I that you have. So you're gonna take the coefficient ai, hit it with the definition of the line segment, it has to be less than bi. So we're hoping we can show that. It turns out this is just some pretty straightforward algebra. So hit do a dot product of AI with your line segment, multiplying out, just some algebra. And then to the next line, a little more algebra. We're just distributing the lambda AI dot product as applied to the first component minus what happens when you apply the dot product to the second component. And then cleaning up some like terms, we have some AI x1s. And so there's really 1 minus lambda of those. And then there's an x2. And so at this line right here, we can now make some statements. We know AI x1 is less than or equal to BI, right? That was by our assumption that x1 was in the feasible region. So this part helps us make this next statement. We're replacing that right there with the BI. So 1 minus that, that's still going to be a positive number, so it doesn't change the direction of the inequality. So we can say 1 minus lambda BI. 1 minus lambda A x1 is less than or equal to 1 minus lambda BI. And that also holds for over here. The lambda AI x2 was by definition in the feasible region, therefore it's less than or equal to BI. These things simplify, so now it's this chain of inequalities shows what we want. This line is the line segment between the two, that's less than or equal to BI, therefore we're done. Okay, again, the key thing, linear constraints form a convex set. Yes, especially tractable case. And linear objectives form an especially tractable set of objective functions. Those two combine to make an LP, great news for us, and that's why the magic of the simplex algorithm that we're going to get to, I'm excited to get to that algorithm, George Danzig's famous simplex. Okay, homework problems from this section, that's 3.4, numbers 14. Homework, we've got number 14, 16A, and 17A, D, and E. All right, almost done chapter 3.